So far we've been working with numbers in exponential form having exponents, and we've been working with numbers in radical form having radicals. Now we're going to have a way to work between the two and really see the relationships that exist. So if I start in exponential form and I have something as x to the 1 over b, I can have a fractional exponent. And what that represents is it becomes x within the radical and b is the index. So the denominator of the fractional exponent is the index within the radical. Now, what if it was a over b, or just another fraction that we had? Well, if I moved the b to be the radical, the a is the numerator, so we could write it as x to the a power in the b root of x, b root, or I could switch and go b root x to the a power. So the a can either be inside the radical or outside the radical. The important part here is that the denominator becomes the radical. We'll say the radical's index. So let's look at some examples before we get into actually solving all of these here. If I said 27 to the 1/3 power, that is the cube root of 27, which hopefully by now we think 27 is 3 times 3 times 3. There's 3 in the set. So 27 to the 1/3 power is 3. 16 to the 3/2. I'm going to write that as the square root of 16, because it's a 2, and to the 3rd. Now you could also write it as the square root of 16 to the 3rd, but what I don't like about that is then I have to simplify, or I have to multiply out 16 to the 3rd and then take the square root of it. Whereas here, the square root of 16 is 4, and then 4 to the 3rd is 64. There are some scenarios where this might be a little bit better, but in this case, I took that route. What if we did 81 to the 3/4 power? So that would be the 4th root of 81 to the 3rd. Simplify the radical, it always makes it a smaller value, then do the exponent. 81 is 3 to the 4th, so that takes a set of 3's out. We'd have 3 to the 3rd, which would be 27. So that means, well, we'll get to another one. 64 to the negative 2/3. Now this kind of goes to negative exponents, which we've talked about before. We're going to take and make it 64 to the 2/3 in the denominator. This is now 1 over the cube root of 64 squared. Now the cube root of 64 is 4 to the 3rd. That becomes 1 over 4 squared, which is 1 over 16. Now what if we then did, we'll do it over here for space, what if we did negative 64 to the negative 2/3? So I'm still going to go 1 over negative 64 to the 2/3, making a positive exponent. This is then the cube root of negative 64 squared. Now although we know with square roots we can't take the square root of a negative yet, we can actually take the cube root of a negative. That's because negative 4 to the 3rd power, negative 4 times negative 4 times negative 4, would actually come out to be a negative 64. So we get here is 1 over negative 4 squared, keeping your parentheses, and our answer is 1 over 16. So just some examples for what we're going to work on these. So now we got 625 x to the 6th, y to the 4th in the 3/4 power. You could go in and distribute in, multiply all of them in, but then you have a likelihood of having 625 to the 3/4, x to the 6 times 3/4, and 4 to the 3 times 3/4. And you might end up with multiple fractional exponents that we don't necessarily want to simplify. So here's another option. Let's change it to make it 4th root of 625 x to the 6th, y to the 4th, and all of that is to the 3rd. So the 4 became the root, the index, the 3 became the exponent on the inside. So now we're going to do a product rule, or a power rule we should say, for the values on the inside and simplify. But before I do that, I don't want to do 625 to the 3rd. That's a way too big a number. 625 is 25 times 25, or it's 5 to the 4th. So instead, I'm going to write 5 to the 4th, x to the 6th, y to the 4th, to the 3rd power. So now we have 5 to the 12th, x to the 18th, and y to the 12th. So for simplifying, when looking at sets, we have 12 fives. Well, 12 divided by 4 is 3, so we can take out 3 sets of 5s with nothing staying in. X to the 18th, 18 divided by 4 is 4 with 2 remaining, so we can take out 4 sets, leave 2 inside. Y to the 12th, divide that by 4, that is y to the 3rd. So our answer comes out to be 5 to the 3rd, which is 125, x to the 4th, y to the 3rd, and then we have the 4th root of x squared. Now normally that answer would be good, but we can actually go a little bit further. If I kind of jump over at the side here, the 4th root of x squared is x to the 2/4, which we saw earlier. We can change it to the exponential. Well, reduce that fraction and it's x to the 1/2. So it should actually be the square root of x. So that's the last thing we'll do. 125 x to the 4th, y to the 3rd, square root x. Now, on our second problem, we take a little bit different approach. We're looking at these exponents and radical forms, and we have to simplify it. I need to find what this value of x is. It's an actual equation. So I'm going to change these to exponential form. So that gives me 7 to the 5/6 times 7 to the 3/6 equals 7 to the x over 6. Now I could look on this side and do the product rule. The product rule would give us adding the two, so that's 5/6 plus 3/6 equals 7x over 6. And then we get 7 to the 8/6 equals 7 to the x over 6. And here, it's not really a solving problem from here because we're just looking, well, if I have 7 to the 8/6 and 7 to the x6, what's x? Well, it just matches up. Our answer turns out to be x equals 8. You're simplifying the left-hand side to be equal to or equivalent to the right-hand side to allow you to then find what the missing value is. A little bit different problem, but it still requires us to use our exponent rules. So let's go to our next page. First thing I want to look at is, can I simplify anything inside the parentheses first? And I can do 24 over 3, which gives me 8, a to the 4th, b to the 3rd, and that's all to the 2/3 power. Makes it a little bit nicer. So from here, this time, let's leave it in, let's distribute in, multiply in the 2/3 and see what that does for us. So we get 8 to the 2/3, we get a to the 8/3 by multiplying, and we get b to the 6/3. Well, we get b to the squared on the bottom. That was where we're obviously at, but we kind of have to simplify this up here. I don't like fractional exponents, so why don't we change this top part into radical form? So we have the cube root of 8 squared, and we have the cube root of a to the 8th, all of that over b squared. So 8 squared we know is, or 8 is 2 to the 3rd, so if we square that, it's 2 to the 6th. So we have 2 sets of 3. Try that again. We have 2 sets of 2's, so 2 times 2 is going to come out. And then for a to the 8th in the cube root, that gives us 2 sets of a's, so that's a squared with 2 staying in. So now as we clean up our answer, we get 4a squared cube root a squared over b squared. Simplifying it down. We don't really want to leave fractional exponents. We want to simplify down till we get to radical form. Could have also then gone through this one and maybe changed it to radical form, all of it at first, and then simplified, but we have different options. Okay, 16x squared to the 3/2 power. That's going to be the square root of 16x squared to the 3rd. Now, 16 is 2 to the 4th, so I'm going to change that first, which then makes it 2 to the 12th, x to the 6th. So now within the square root, I have 2 to the 12th gives me 6 sets of 2, so 2 to the 6th comes out, x to the 3rd comes out, and then when we multiply that, we get 64 x to the 3rd. Next problem, the 4th root of 16a to the 4th, b to the 8th, to the 3rd. Well, 16 is 2 to the 4th, so I'm going to change that Then I'm going to do the power rule. I get 2 to the 12th, a to the 12th, b to the 24th. Inside the fourth root, that's going to take out 3 sets of the 2's. It's going to take out 3 sets of the a's, and it's going to take out 6 sets of b's. For our next problem, I'm going to simplify inside the parentheses first. We get 27j to the 6th over k to the 4th, and that's to the 2/3. We're going to change this now to radical form. It's the cube root of 27j to the 6th over k to the 4th, and all of that is squared. 27 being 3 to the 3rd, we're going to go 3 to the 3rd, j to the 6th, k to the 4th, quantity squared. Now that's going to be 3 to the 6th, j to the 12th, k to the 18th. So simplifying, 3 to the 6th, I have 2 sets of 3's coming out. J to the 12th, I have 4 sets of j's coming out. And k to the 18th, I have 6 sets of k's. So we'll say 9, j to the 4th, k to the 6th. Our last two problems are the equations we were looking at earlier. For this one, we're going to change it to exponential. So it's 7 to the 4/3 over 7 to the 6/9. But I want to subtract, I want to use quotient rule. In quotient rule, we subtract, but I need common denominator, so that's going to be 4/3 minus 2/3, which leaves me with 2/3 on the left-hand side. So when that's equal to 7 to the x/3, we get x equals 2. The next problem, I have 4 to the 9/4 times 4 to the 1/4. Together, that's going to be 9/4 plus 1/4, which gives me 4 to the 10/4. Now I could reduce that and make it 4 to the 5/2. It's just a fraction that reduces. But over on this side, I have 2 to the x. Well, let's make the left side match 2. So if I change that to 2 squared to the 5/2, because that's what 4 is, it now becomes 2 to the 10/2, or 2 to the 5th, equals 2 to the x, so x equals